Okay, so welcome to the learning series session. So the first speaker is Simon Du. Professor Simon Du right now is an assistant professor at the University of Washington. His research interests are broadly in machine learning, such as deep learning, representation learning, and reinforcement learning. So before the faculty, he was a postdoc at IAS, the Institute for Advanced Study at Princeton, and he completed his PhD in machine learning at CMU. And prior to that, he studied at UC Berkeley, and also he spent some time at Simons Institute at Facebook, Google, and Microsoft. So today he's going to talk about something related to representation learning. So let's welcome Professor Du.
All right. Thanks for the introduction. Should I start?
Okay. Yeah, sure.
Okay. Thanks for the introduction. I'm very happy to be here. So today I'm going to talk about some theoretical results about representation learning. So representation learning is very related to neural network. It's been very popular in recent years. So we all know that neural networks have been very popular in many applications. For example, for computer vision tasks like image classification, we can use convolutional neural networks. For bioinformatics, like those classifying molecules, we can use graph neural networks. We can use recurrent neural network, attention-based neural network for natural language processing tasks, like machine translation. And generally, we can use the most basic neural network, fully connected neural network for feature-based data. For example, here we want to predict the price of an apartment, and we can use some features like size, number of rooms, age as features. Also, for reinforcement learning, we can use policy network and Q network to model the policy of the net or the Q function. So we all know that these, basically neural networks have been very popular in all these kind of applications. So today I'll focus on one particular usage of neural networks, or generally a particular paradigm in machine learning, and which is called the representation learning. Okay, so I'll give you a concrete example here to show how representation learning is working and why it's very powerful in a computer vision task. So this is a paradigm in representation learning at a high level. So here, let's say the step is the following. We first train a neural network, let's say ResNet, usually very complicated neural network, on ImageNet, where there are 1 million data points and 1,000 classes. Okay, and then we call it representation or a feature extractor, the mapping from the image, for example, this cat, to the second to the last layer of this neural network. Okay, so here this is the hidden layer 3. Okay, so we call this vector output vector a representation of the this cat image. Okay, and we also call, or sometimes we call this representation function as the mapping from this cat to this vector. Okay, so you can also call it the feature extractor. So we train this function, the representation function, through training a neural network on the image end. So this function is really represented by a very complicated neural network. Okay, so this is the representation function and how we train it. And how do we use this representation? It's very easy. We just view it as a feature extractor. For example, here for a new task, let's say we want to classify dogs, or the image is not dog or not. Let's fix this representation. So it's mapping from this image to the vector, and we just retrain the last linear layer. Okay, so we'll fix this previous first, say, 3 layers, and then we just in this figure. And then we just retrain the last linear layer. So basically here, this is a linear classification problem. And then because the hope is, because this learned representation is very informative and compact about this image. So here we can use kind of a small dimension, reduces original problem to a small dimension problem. And this linear classification on top of this learned feature extractors are already very discriminatory in classifying this image. Okay, so this is how we do and how we learn the representation and how we use this representation function. So here, let me give you a more concrete example. So here, let's say we use this representation learning strategy to train a representation on the ImageNet. Okay. Remember, there are 1 million data points and 1,000 classes. So in this talk, I will interchangeably use task or class. So they are basically the same thing. Okay. And for the target task, this is what we really care about. It's a few-shot learning task on the VOC7 dataset. So this dataset is, or this task is called few-shot learning because there are 20 classes, but each class only has 1 to 8 examples per class. So it's very few data per class. All right, so here's the result. So if you don't use representation learning, so basically you can only use this 1 to 8 examples per class in your data, then whatever method you can use, like neural network or even classical methods like kernel method, linear SVM, this kind of methods, you can only achieve 5% to 10% accuracy. Remember, this is a 20-class classification problem. So even if you do random guess, you can have 5% classification accuracy, right? But here, if we use representation learning, so first we train a representation that learns the, some good features about the image in general, and then we use the linear classification on top of it. Then we can achieve 50% to 80% accuracy. So you can see here, this is a huge boost of the performance because we use representation learning. All right. So in this talk, I'll focus on why, trying to understand, build a theory about why representation learning is so powerful in improving the accuracy. So beyond computer vision, there are also other representation learning is widely used in many applications. For example, in natural language processing, we often use a sequence model, and each hidden state can be viewed as a representation about a sentence or like a word. Also, for graph representation learning, we can embed a node to, let's say, a low-dimensional or sometimes high-dimensional vector, and this vector is a representation of this node. And this representation is learned through, sometimes through a graph network, which aggregates the adjacency nodes information. So you can check out this paper by Benjo et al. In 2012, which gives like an overview about representation learning. So here, there are 2 questions I want to answer today. First, I want to study what are the necessary and sufficient conditions that help representation learning improve the classification accuracy. Okay, so why do we say what are the necessary and sufficient conditions here? Because we, without any assumption about the source tasks that help you learn representation and the target task, you cannot hope for any theoretical guarantee or any, even in practice, cannot hope for improvement if you don't put any assumption about these 2 tasks. So we do need some conditions that we want to characterize to show that under these conditions, representation learning probably improves this efficiency. And secondly, we also understand why it's the case, like what is the underlying mechanism that help you from theoretical point of view that help representation learning learn a good representation. All right, so let's begin. So here I do need some notation in order to fully discuss the results. So here, this is a setup. We have source tasks and target tasks. Let's say we have in total big T source tasks, okay? And the architecture is the following. So you use x1 to x big T to denote the samples from different tasks, okay? And first, we'll have, to learn representation, we'll have shared representation, shared function H, okay? So this is a common representation. So every input from every task will go through this representation first, okay? And then this layer, the second to the last layer, is the representation for different tasks. And for different tasks, we will train a different task-specific predictor. Let's call it G1 to GT, okay? So this can be very different, like different linear classifiers for different tasks. Okay, so after we learn this representation, so we fix this function h. In the target task, we'll just retrain the last linear layer, which I'll call it f. Okay, so now let's discuss a bit about what are these functions. So oftentimes in practice, G1 to GT and this f is like a simple function class or simple functions. For example, they are the linear classifiers. Okay, this is what happens in practice as well. And sometimes you can use a slightly more complicated neural network to represent these functions as well. On the other hand, this H function is often a very complex function, like multi-layer neural network, like ResNet, or even BERT transformer in natural language processing. Okay, so I'll use this big G to denote the function that's for the prediction class and big H for the representation class. What you want to know is that big H is often very complicated, and big G is more or less very simple. Okay, so this is a more formal procedure. Let's say for each task, each source task, we have N1 data. Okay, and it will denote this X1T, Y1T. So this is one pair of data to X N1T to Y N1T. Okay, in total, NT is from 1 to big T. So these are the data from the source task. Okay, so and then to learn the representation, we'll solve this bilinear. Bi-level optimization problem. So you can see here in the outer loop, we have minimization or representation function based in big H. And inside of this outer loop, we have for each task, we are trying to find one prediction function that can minimize this loss. Okay, so this loss, we can take product loss or cross entropy. And GT, the composition of GT and H is your prediction. Okay. And then YT is your label. So we use the loss to measure the performance of your predictor. And for the predictor on the target task, oftentimes we assume that we have N2 data from the target task, and N2 is much more than N1, and this data are sampled from some distribution mu. N2 is more than N1 is very is what happened in the fusion learning task, where N2 is basically 1 to 8, but N1 is about 1,000. And for training the target task, again, we will use this loss function, but here we only train the last linear layer, F. Okay. And here, importantly, we'll fix this H, the learned representation function. So this is a setup. All right. So what would be an before going to the theory for the representation learning, let's first give a few review about what is the standard statistical learning theory. So if you only train your model from the target, using the data from target domain, basically you're solving this optimization problem. You're optimizing over both F and H, and then using the data, only this N2 data in the target domain. So this is the standard theory tells you. So we can have the expected loss, okay, with respect to this underlying distribution mu that generates the data. The expected loss can be bounded by CH plus CG over N2. Okay, so let me explain what are these terms. So CH and CG are some complex measure of the representation class and the predictor class. You can use, for example, number of variables, or more generally, VC dimension to characterize this complexity of the different function classes. We can also use the Markov complexity or Gaussian width to as a complex measure as well. So this is what you can get for you only using the data from the target domain. All right, so what would be an ideal theory for the transfer learning or representation learning? So ideally, you want to identify a set of natural assumptions such that if this data satisfies the assumption, representation learning probably helps, and without this assumption, representation learning does not help. Okay, so this is an ideal form of the theory. Like the expected loss is bounded by CH over N1T plus CG over N2. So why we can expect a theorem like this? Because to learn the representation, we really use all the source data from the source domains. And in total, we have N1T data. Remember, we use this data to learn the representation. So we expect instead of N2 being the denominator, we have N1T in the denominator. that represents that we use all the N1T data to learn the very complicated representation function. And for the second term, is somehow unavoidable because you do need, for learning this linear classifier, you only use N2 data. Okay, this is what we hope to get. So you can compare with this bond with the bond in the previous slide, which is CH plus CG or N2. So you can see here, if N1T is much bigger than N2, we have much better bond than the standard statistical learning series suggests. Okay. So the following we'll discuss when we can have this ideal bond. What are these natural assumptions, and when these are necessary. So the first assumption is called the existence of a good representation. So this is a pretty natural assumption because this is why the fundamental reason why we use representation learning in the first place. Basically, we assume that there's a shared good representation that for all the source task and the target task. And more formally, there exists a representation that's called H star that in this function class, and several predictors G1 star to GT star and F star in this predictor class G, such that the composition of GT star and H star have zero loss. Although the composition of F star and H star has zero loss as well. So here we assume zero loss is just for simplicity. You can also generalize this theory to the setting that we have small loss instead of zero loss. So this is very natural assumption, and without this assumption, you should not use representation learning in the first place, right? Because if you know that repetition, there's no good repetition that is shared for both source task and target task, then any representation you learn is not going to be helpful in the target task. The next natural question is whether this assumption alone is enough to prove that representation learning is helpful. So here, let me give you an intuition why this assumption alone is not enough. Okay, so here's an intuition. Suppose your source task is about classifying different types of cats. Okay, and so you can use this cat images to learn representation. However, the target task asks you to classify whether an image is a cat or a dog. So in this setting, with this problem setup, you cannot hope that your learned representation is very helpful for the second target task. The reason is that the source task can help you to learn a good representation with this representation function feature structure for cats. So given a cat image, you can use the representation function to have a very good representation of vector that represent the cats. However, in the second task, you do need to have a good representation for both cats and dogs. Okay. However, your representation only are good for cats, so these are not good for dogs. So that's the learned representation may not be very helpful in the second target task. Although there might exist one good representation that's good for both cat and dog, but you may not identify that one. So these are some more formal example. Let's say the input is a 1,000 dimensional 01 vectors. So the good representation, the underlying good representation is the first 100 dimension. Okay. So all the tasks, including source and target tasks, only need the first 100 digits to for accurate prediction. For example, the task can be whether the 10th digit is 1, predicting the sum of first 100 digits, etc. So basically, the good representation is first 100 dimension. You only need to use first 100 dimension. So the bad scenario will be the following: the source only need to use the first 50 digits. For example, whether the 10th digit is 1, things like tasks like this. So you can use this kind of source task to train the good representation. So you will identify that the first 50 digits are very helpful, but you don't know whether the 51s to the 100 digits are helpful or not. Okay, so it's very hard to identify whether those digits are good or not, or are useful or not. However, the target task need to use all the first 100 digits, for example, predict the sum of the 100 digits. So in this bad scenario, you know that the first 50 digits is useful, but you don't know whether 51 to the 100 digits is useful, so you not use those information effectively. So basically, in this setting, the source text cannot give the full information about this good representation. The full information in this problem is the first 100 digits, but the source text only gives the information about the first 50 digits. All right, so here's our proposed assumption to avoid these five scenarios. This is called the diversity of the source text. Basically, we require the source text to cover the whole information about good representation. So the main question here is that what is the formal definition of this diversity? So here's our assumption for the linear. Let's first focus on the G function being the linear prediction class, which is also the focus of this talk. So the assumption is the following. There exists a representation, this is the first assumption, that there exists H star in H such that H star with any input is in RK, okay? And also for these linear predictors, we'll have the W1 star to WT star and WTA star that's also in RK, such that the composition with inner product between WT star and H star of an input XT has zero loss with respect to the label YT. Okay, and similarly for the target task. So this is just rewriting of what the first assumption, the existence of a good representation. And the second assumption is more important and more non-trivial. It's the diversity of the source text. So here we view the diversity as the following. So let's say this big W star is a concatenation of all the source text. So this W1 star to W big T star is it's a matrix of size K by big T. Okay, we assume this matrix is of full rank. So here implicitly we actually need the number of tasks bigger than K, which is a dimension of this embedding or this representation. So being in the full rank intuitively means that it can cover, this T task can cover the whole span of the good representation. That's why we call it kind of, it's also kind of diversity. So as long as the optimal predictors cover the whole span in this K-dimensional space, then we can have some good results. So this is a formal definition of this diversity assumption. All right, so here let's look at our results. So let's first look at the linear representation class, which is like the simplest class you can think of. Basically, you have input X, which is in D-dimensional, and the linear representation is just a matrix of size K by D, where K is much smaller than D. So the first assumption becomes there exists a B star of size K by D, and these linear predictors, these W's and these laws are zero for both the source and the target task. Okay, and then under the two assumptions, so we also, beyond this first assumption, also assume this W star, the concatenation of these W stars is a full rank. Then we can really show this bond like this. So the expected loss is bounded by dk over n1t plus k over n2. Okay, so this is pretty much the ideal theory we want, because without representation learning, this is pretty about learning a linear predictor in RD. So that one you can get a D over N2 bond. So if you compare these two bonds, we assume that the K is much smaller than D. For example, you can think about the example I give to you about this digits, and D will be 1000 and K is 100. And N1T often we assume is very big. So the first term, if you compare the first term, it's much smaller. Even N1T is much bigger than N2. A second term, K over N2 is much smaller than D over N2. So in compare these two bonds, in this case, we show that representation learning probably helps. And you can also notice that this is pretty much the ideal bond, because to represent this representation function, you do need dk parameters. And in this bond, we have dk over n1t. So you do have this, basically this term represents that you use all the n1t data to learn the representation function. So this is a simple example for linear representation. We also have a more general result for general function class, which includes, you can use it for neural network as well. So here this is our assumption. So here with a more abstract notion, we assume there's a H star in big H such that the composition of H star and the W's have zero loss. And then, again, under the assumption that this big W star has full rank, then we can have this kind of form. So instead of decaying the linear representation, we'll have CH over M1T, where CH defines the Gaussian width of the representation class. So it's a complex measure of the function class, measure how well the function can fit the noise. You can also plug in other function complex measure, and including those of neural networks. So basically, this shows we can extend this theory to some general function class as well. All right, so a quick comparison with previous work. So this is our bond in the linear setting. There's a previous work by Maurer et al. 2016. They also assume assumption 1, but they also assume that another assumption is different from our assumption 2. They assume that all the tasks are sample ID from some distribution over the task. And they can obtain a bound like this. It's T dk over T instead of N1T like ours. So in this sense, our bound is better, but of course we have a different assumption. But their bound, the drawback of their bound that their bound does not show that you use all the source data to learn representation, because the denominator is T instead of N1T, where in total you have N1T data in the source task. So we believe that our bound is somehow more realistic in practice. Also, in this assumption, they show that this 1 over T is tight. So you cannot avoid this 1 over T term to improve it to 1 over N1T like ours. So here's an brief explanation of why this, what's the underlying mechanism. The really fundamental reason is this bi-level optimization, that you are jointly minimizing both the representation and its predictors. So, and the main idea is that the optimization of representation is over all the tasks. So you do need to find a good shared representation for all tasks. Otherwise, the loss cannot be small. And we assume there exists one, so you can find one through this optimization problem. So, okay, so this is basically the key message of this talk. So the existence of good representation and this diversity of tasks are the key conditions that help representation learning to improve sample efficiency. So I don't think I have time, but I'll just tell you that there's also extension about our work beyond this supervised learning setting to this linear bandit setting, and I also think Li Wei and Qi Jin, they also have results for reinforced learning as well. So I'll ignore this part. And in summary, the existence of good representation, this diversity are the key conditions. And the fundamental reason is that this bi-level optimization problem formulation forces you to learn good representation. However, for now, the open problem is that we still don't have an optimization theory for representation learning. Representation learning usually involves a non-convex optimization problem, but here we don't have a very good theoretical understanding of it. Also, we can also extend representation to other settings. We talk about bandits, and there's also other directions like reinforced learning, control, etc. So I would like to conclude here and take some questions.
Thank you, Simon. Very nice talk. Very nice result. So I have one question. So in the few shot setting, or maybe the people even consider zero shot setting. So the N2 can be very small, right? So yeah. Even zero. So in that case, we can still achieve some accuracy. So but it seems that at least you require N2 is larger than maybe the number of linear layer, parameters in a linear layer. So how, is there any idea on this or any thought?
Yeah, so that's a great question. So essentially, we don't. So in practice, you're right that only using like 1 to 8 examples in the future learning can already learn a very good predictor, and usually K is much larger than N2 as well. In that setting, actually, instead of using the theory we use here, basically we are using linear regression theory where K or N2 is tight. For classification, you can use some other margin-based theory. I think that's more related, and that you can obtain some dimension-independent bound. So that will be more appropriate to characterize setting there. Also, people use some nearest neighbor kind of method in few-shot learning, and that can reduce, with some proper assumption that can reduce sample complexity there. So I think that part is more or less separate from what I'm talking here, because that part is like, why in high dimension, you can still have a good sample complexity, and you can obtain dimension independent here. I think if you use those theory and combine with ours, you can still get reasonably good theoretical results. But that's a good question.
Okay, so the second question related to the assumption 2, so the diversity assumption. So did you check whether it's satisfied in practice, or maybe in say computer vision applications?
Yeah, I think we did try on some language models that you can see at least it is full rank. Although the least singular value is kind of small, so I think this also hope to obtain some more fine-grained bounds. So here, the full rank here is for the worst case target task, but if there's more assumption, more connection between the source and target task, you may have a more fine-grained kind of assumption about this diversity that's more related to both the source and target task. But here, our assumption only related to the source task.
Oh, I see. So the condition number, so it's hidden in the bigger...
Yeah. I didn't talk about here, but there's a condition number dependency there, right?
Thank you. So any other questions from Zoom? So actually, we have a lot of audience from other online platform. So so they cannot ask question here. Okay, so if there are no other questions, thanks, Simon.